So let's look at an example of normal stimulus and response for IPv4. Pretty simple. Here we have two systems, System A and System B. They're both in the 192.168.0 network, and their IP addresses, System A is 22 and System B is 33. So we have different IP addresses on the same network. And generally speaking, when you see communication between devices with IP addresses, you're going to get what you expect to see, right? The source IP is in the source IP box. The dest IP is in the dest IP box. When communication goes back the other way, then you reverse them. Now, again, keep in mind, IPv4 is not a reliable protocol in the sense that it doesn't have mechanisms that make sure packets are delivered. So unlike TCP, where we get acknowledgments that things were delivered, we don't get that in IPv4. So because of that, you get a lot of one-way communication. So there's nothing that says you have to get a response back. So even though I have two things on the screen here, you could very much just as easily just have the one, and that would be perfectly acceptable depending upon what the transport layer protocol in use with IP was. If it's UDP, you could definitely see something like this. If it's TCP, you'll get some type of acknowledgement back, in which case the source and destination IP addresses will be reversed as they are in this specific example. Let's look at another example of normal stimulus and response based upon some of the concepts we talked about with network address translation. So in this case, we have System A and System B again. System A has an internal address of 192.168.0.22. System B has an external address of 62.32.14.95. So you can think of that as something just out there on the internet, maybe a public-facing web server. In between those, we have a router, and the router has two interfaces on it. It has one that is facing downstream towards System A, and that's 192.168.0.1. That's its address on that interface on that network. And then it has an external interface with a external address, 62.32.14.91. In this case, System A wants to communicate with System B. Now, what's going to happen here is the source IP, System A, is going to send a packet to the destination address of 63.32.14.95, System B. Now, what's going to happen is System A is going to recognize that address, that 6332 address, is not on its local subnet. So what's it going to do? It's going to send it to its default gateway address. In this case, the default gateway address is 192.168.0.1. Now, you might be looking at this and saying, wait a minute, if I'm sending this and the destination IP is 63.32, how is it getting to the router? Because that's not its address. It doesn't know, what that, or at least it knows the address, but it's not its address. So how does it get there? Well, keep in mind, System A and that router are on the same network. So when two devices are on the same network, they don't have to have IP addresses to communicate with each other. They can communicate via the data link layer, layer 2 MAC addresses via Ethernet. So it knows the MAC address of the router. So even though the IP address is that 63.32 address, the MAC address it's going to be pointed to is the one of the router. And we'll look at that as an example here in just a moment. Now that said, the router gets that packet on the internal interface, and it takes the packet and modifies it. And you would think normally modification of a packet isn't a good thing, or maybe that's a security issue. But in this case, it's perfectly normal, and it's what every router on the internet does. It takes that packet and modifies it and takes the source IP address out of it and replaces it with its own source IP address. And it creates an internal table where it keeps track of these things. And it has to do that because when it communicates with System B will not be able to talk back to 192.168.0.22. That's a non-routable IP address. It has to communicate directly with the router, and the router itself is going to maintain the record of all of these mappings it's done, all these mappings between internet, external and internal IP addresses. So that's what we have going on here. The destination IP address remains the same, but the source IP address is getting rewritten by the router who's keeping track of that. Once that's done, we see the same process happen back in reverse. System B sends a reply back to the router. The dest IP is that router's IP address. The router checks its internal routing table. It sees that the response in this particular communication is destined for 192.168.0.22, which is System A. And then it rewrites the packet appropriately, replaces the IP addresses, recalculates checksums, and we'll talk about checksums here in a minute, and sends that packet on to System A. So it's this rewriting of packets, this network address translation that's going on that allows for the normal stimulus and response of routing packets across the internet. And this is just a simple example. We just have one intermediate router, but you can have dozens of intermediate routers, and the same process is just going to happen over and over again with packets being rewritten and all these different routers keeping track of this packet and its internal routing table along this specific path. Before we move on from IP addressing into some other features of the IP protocol header, there's one question I get asked often, and I want to make sure I clear that up and try to answer that as best I can. And that question is, how do I know what's an internal address and what's an external address? After all, I keep referring to internal addresses and saying they're not routable. So how do you know what those addresses are? Well, that's something that's defined by the Internet Assigned Numbers Authority, or IANA, the same organization that manages the distribution of unique external IP addresses across the world. So IANA is defined via RFC 1918, a set of internal ranges that can be used within internal networks that are not routable on the Internet. And what they're basically saying is that no unique IP addresses will be assigned to host out on the internet in these ranges. So these are what you should use within your networks, hoping that most networks will be able to use these effectively, that there's plenty enough of IP address spaces here if you subnet appropriately. And for the most part, that's generally how it is. So you see here we have three ranges: 192.168.0.0/16, 172.16.0.0/12, and 10.0.0.0/8. We haven't talked about CIDR notation, CIDR, classless interdomain routing. That's what this notation is, where we have an IP address / a number. That number is actually referring to the available portion of the packet for the number of bits that are available for the network side of the equation. So in this case, if you see 192.168.0.0/16, it's saying 16 bits of that are the network portion of the address. An IP address is 32 bits. So in this case, the left two octets of the dotted quad are, in this case, the network portion. Same with the /12, same with the /8. For 10.0.0.0/8, it's saying only 8 bits are reserved for the network portion of the address. So 10 dot, that first octet is the network portion, the rest are for individual hosts. So these specific ranges are what you can use for internal networks. Now, with that said, how do you define external networks? Well, there are a couple ways. First of all, you might say, okay, is everything else available for external assignment? And for the most part, that would be the case. Now, there are sections that are quarantined off for other specific uses. There's a multicast range that's used for multicast traffic. There's some reserved IP space that's used for testing, a few other things. There's the broadcast address, so on and so forth. So there are things that are reserved beyond just the RFC 1918 addresses, and you can look those up on the IANA website. But for the most part, other than those things that are reserved, anything that's not an RFC 1918 address is assignable out there on the internet. Now, of course, one of the big problems with IPv4 is there are only so many IP addresses to be handed out. We're running out of them. We're running out of them quite quickly, and that's why the move to IPv6 has kind of hastened a little bit, or at least some folks would like to think it has. Maybe it hasn't, but we're trending in that direction, wherein we need to move to IPv6 because it has a larger addressable space. There are more unique addresses that can be assigned to quite a magnitude. So again, when we're talking about external internal addresses, anything in these RFC 1918 internal ranges are non-routable. Those are what you're going to be using for internal networks, which you're going to see most of the time. And everything else, unless it's otherwise reserved, is going to be an external IP address. And that's important to keep in mind when you're thinking about stimulus and response related to IP traffic. So now let's look at some packets that actually show the IP protocol in action. Here I'm looking at http://google.pcapng, so it's a packet capture you should have access to if you want to look and follow along as well. Now in this case, this is a TCP transaction, but as we know, TCP relies upon the IP protocol to work. So I've got the first packet selected here, and I've gone down here, and actually you see the Internet Protocol version 4 as one of the packet headers. You see that highlighted down below. I'm going to go ahead and expand that. We see a couple things we've already talked about. We see the IP version is 4. We see the header length is 5, which means you multiply that by 4, and you get 20 bytes. So we have a minimal length, the standard 20 byte packet header. If I click on this, and you see down below in the packet bytes window, you'll see that that 20 bytes are highlighted there, and that's confirmed down here where it says IPv4 20 bytes. So we have those fields. We have a couple of other things we talked about. We have total length, which talks about the total length of the packet. In this case, it's 52 bytes. And then we also down here have our addresses, which is what we've talked about before. Now, this is an important example that really shows the normal stimulus and response of communication out to the internet. Here we have a source IP address of 172.16.16.128. That's the internal IP address on a local network. That's a non-routable IP address. We have a destination address of 74.125.95.104. Presumably, since this is called HTTP Google, that's a Google-owned IP address, and I can tell you it definitely is. So that's our destination address. So we're sending to that. Now in this case, 172.16.128 doesn't know how to communicate with that device. That's a device outside of its network. So again, what do we do when we need to communicate with a device outside of our network? Well, we send it to the default gateway on the network. So in this case, the default gateway, we don't necessarily know what the IP address of it is. We don't see it right here, but that doesn't really matter. We're not communicating with it by IP address. We're actually communicating with it up here. And if you look at the Ethernet header, we have a source and destination IP address, a source and destination Ethernet address here. And we look at this, we see a destination address. We can't really make a lot from that, but watch this. I'm going to go in here to edit preferences. I'm going to go to name resolution. I'm going to tell it to resolve MAC names. And when I do that, it's going to tell me that this is a MAC address that's associated with D-Link. Well, what does D-Link make? Well, they make a lot of networking gear. Specifically, they're known for making switches and, you guessed it, routers. This is actually the MAC address of our router. So this packet's being sent to the router on the local network, and it can do that because the router's on the same network, and we don't need an IP address to communicate with that. We can do that with Ethernet addresses alone, and that's what's being done here. So that's the handoff that's going on there. That confuses a lot of people. How am I communicating with my router if the router's IP address isn't in this packet? That's okay, and that's because of the MAC address as it exists here. So this is an example of normal stimulus and response with an IP packet, and specifically one that's going out to something on the internet. Kind of a crash course in how IP packets are routable. Not too overly complex. That's one of the beautiful things about IP. You can do a lot with 20 bytes. In this case, not even using all of them, we're effectively getting packets from one side of the internet to the other. Now, doing that reliably, that's a little bit more challenging, and we'll talk about that when we dig into transport layer protocols later.